this event, of course, on where he will continue explaining to us properties of group of germs of diffeomorphism. Please, Javier.
Thank you very much. We are going to see, if we have time, at least one application, maybe two, of this theory of how you can apply the algebraic theory of local diffeomorphisms to the context of other problems. And last day we announced a theorem of G's, which probably a theorem that he did in IMPA, that says that if you have a group of real analytic diffeomorphisms of the sphere, such that besides this property is nilpotent, so you have that the second derived group, which is just the derived group of the derived group, is trivial. And this is called in the paper being metabelian, right? So I'm going to try to give an idea of the proof of, let's say, maybe the main case of the proof. In any case, both cases are similar, so yeah, no problem with it's a very relevant case. So obviously, if G is abelian, there is nothing to prove. The derived group is already trivial, so we can use a result here in the case that G is not abelian. We can use a result that is very classical in the theory of nilpotent groups, which is that every non-trivial normal subgroup of an nilpotent group contains an element of the center. So this group over here is non-trivial by hypothesis, because in the complement things are obvious. For us, the theorem is. This is working? There exists an element in the center of the group that belongs to the derived group. Why I chose the derived group? Because the derived group is contained in the subgroup of G of diffeomorphisms that are orientation preserving. Just because of that. I mean, it's because this is contained in the intersection of the center of C with the orientation preserving diffeomorphisms, because a commutator is always of this form, right? And the number of orientation reversing elements in here is always odd. If F is orientation reversing, so is the inverse, so it's always even, sorry. So the composition is actually orientation preserving. What happens in this case is that we know that because the diffeomorphism is orientation preserving, the fixed point set is actually non-empty. All right? And because of the left-hand number of the map is equal to the Euler characteristic, which is 2. And besides that, the other property, this is just a consequence of being orientation preserving. Now we can use that it's in the center, and that means that for any other element of the group, this set is actually, invariant, no, sorry, F. Yeah, if G commutes with F, G preserves the fixed point set of F. That's something very easy to prove. So here, this shows that this is going to imply that our group has a finite orbit. I'm not going to do that with all detail. I'm not going to do that with detail because there are several topological results, a couple of Brouwer theorems, properties of the real analytic diffeomorphisms of the circle. Nothing very difficult, but there is a combination of topological things. It's obvious in some cases. It is obvious if the fixed point set is finite, and obviously non-empty. But that's obvious because we already said that it's non-empty. So it's obvious if it's finite, and it's obvious if this set is a real analytic set, okay? Because that's one of the places in which it is used that we're working in the for groups of real analytic diffeomorphisms. So this set over here is a real analytic. And it is also obvious if the singular set of this is non-empty. Because this set is going, obviously this element over here has to be non-trivial. Okay, I think I said it, but I didn't write it. There is a non-trivial element in the center. So this real analytic set has dimension 0 or 1, because it's not S2. And if it has a singular set, for instance, if it has a component like this would be a singular set. The singular set is always going to be 0-dimensional, so a finite collection of points. So obviously that would be an invariant subset, a subset that is finite and invariant by the whole group. Because if all the elements of G fixed this fixed point set, they fix the singular set of the fixed point set. So the unique case remaining is the case in which the fixed point set is a disjoint union of circles. Something like that. And that's the part that I'm not going to do. He uses some topological results, not really, as I said, things that are well known. For instance, the Brouwer theorem that says that if you have a map from the closed X to itself, then it has a fixed point. And some other results of Brouwer are a little bit more sophisticated to show that indeed G has a finite orbit. I'm not going to do this part, but it's something these days that is even well known with much less regularity. If you consider an nilpotent subgroup of diffeomorphisms of the sphere of class C1, it has a finite orbit with at most, if it's at most 4 elements. If it's of orientation preserving diffeomorphisms, it has at most 2 elements. So these days we know that these finite orbits are indeed small. There are finite orbits of a small size. But I'm not going to prove this last case. So what we have is that there exists a finite, non-empty, finite orbit. That it's a G invariant set. It's invariant by every element of the group. Right? That's what we have. And we can consider H, which could be the subgroup of elements of G, such that they fix every element in this invariant set. This is obviously a subgroup. It is clearly a finite index normal subgroup of H, because the quotient is isomorphic to a subgroup of bijections of the orbit, so of bijections of a finite set. So this subgroup is finite. Okay, I'm going to call it J. I'm going to use H for something else. And in particular, we can apply what we know to this group J, because now we can fix a point in that orbit. And since every element of J actually fixes P0, what we have is that G can be interpreted as a group of germs of real analytic diffeomorphisms of the sphere in a neighborhood of P0. If you want, there is a map from J to this that is just considering the germ in the neighborhood of P0. But this map is injective because of the open mapping theorem. Another place in which we are going to use that we are working in the real analytic category. If two diffeomorphisms are the same, are coincide in a neighborhood of 0, then they coincide in the sphere. And obviously, you can complexify here and see this as a group of local diffeomorphisms in a neighborhood of a point that we are going to call 0 as usual. So you can see J as a subgroup of local diffeomorphisms. And if you prove, for instance, that G is metabelian, by using properties of, you can actually transfer your problem to this group of local diffeomorphisms. But as I said yesterday, I think, one of the ways in which we try to do this transfer is actually by linearizing these problems. And this means in particular that instead of working with the group, we prefer, if possible, to work with the Lie algebra. But as it happens with the usual theory of Lie groups, the Lie algebra doesn't generate the whole group. It generates just the connected component of the identity. So we have this group over here, a priori, as a subgroup of local diffeomorphisms, is not necessarily connected, meaning the Zariski closure is not necessarily connected, so we can actually make it connected by considering something smaller. And that's what H appear. We consider the connected component of the identity of the closure of J intersection with J. This group over here is still a finite index subgroup of J, and in particular of G, because this group, the connected component of the identity of J, we already saw is a finite index subgroup of the closure of J. So we are going to have this. And this group is, I think, it's, if you consider the closure, we have also this. H is of finite index in both J and G. So if, since it's of finite index in J, it contains its connected component of the identity, the connected component of the identity of the closure of J. But obviously, this group over here is Zariski closed, so the closure of H is contained in there. So they are the same. So roughly speaking, the closure of H is connected, so it coincides with. And so, resuming what we just did, we work at the beginning with any group of real analytic diffeomorphisms of the sphere that is nilpotent, and in the process, we are considering the problem for something different, for a group that is kind of big in G, but it's not the whole G. It's a group that we can see as a group of local analytic diffeomorphisms, and that when we consider the closure of that group in here, it's going to coincide with its connected component of the identity. Why we want that? Because of the Lie correspondence. What's going to happen is that H is going to be metabelian if and only if the Lie algebra is metabelian. Right? And that's where we are using that this is connected, because the Lie algebra doesn't see what happens outside of the connected component of the identity. So we just have to prove the theorem for H, not for E, we just have to show that if you have a Lie algebra that is nilpotent, a Lie algebra, this Lie algebra is going to be a Lie algebra of formal vector fields in dimension 2. We just have to see that if you have a Lie algebra that is nilpotent, because it's because these algebraic properties are preserved when you go to the Zariski closure. So if G is nilpotent, this J is nilpotent because it's a subgroup of G, then the closure is nilpotent because the closure of a group is nilpotent even only if of local diffeomorphisms, if and only if the closure is nilpotent, and so we get this one over here is also nilpotent because it's contained in the closure of G, that is nilpotent because G is nilpotent, so all these properties are preserved, and what we want to prove is that a Lie algebra that is nilpotent is metabelian. This is easy. And I wanted to do this proof, even if it's easy, just to see how this theory actually gets to a place in which maybe we're not working anymore with a Lie algebra of vector fields. These guys over here can actually be represented by formal power series that are divergent. It's perfectly possible it happens most of the time. But still, we can do some calculations. We can use the structure of this Lie algebra in order to prove the result. So the lemma is that if you have a Lie algebra of formal vector fields, in C2 that such that this Lie algebra is nilpotent, then it's metabelian. The definition of the derived Lie algebra and the second derived Lie algebra is the same as you have for groups. In groups you have the commutator, in Lie algebras you have the Lie bracket, but the definition formally is the same. So we want to see this. And there are several cases over here. Obviously the most simple case is if the center of our Lie algebra is trivial. It's simple because then the Lie algebra is trivial. As I said, this is a property of nilpotent groups, nilpotent Lie algebras. Every subgroup, every subalgebra, every normal subgroup, or in this case, every ideal that is non-trivial, contains a non-trivial element of the center. So if the center is trivial, the Lie algebra is trivial, and obviously this is. The point is trying to understand what happens with the center of the Lie algebra. If it's non-trivial, the second case, we are going to suppose that you have two formal vector fields, that they are independent over the fraction field of the formal power series, of the ring of formal power series. Yeah, but this is because if you consider this, the formal vector fields, and you consider the tensor product with this fraction field, it becomes a vector field over this field which is of dimension 2, because there are every vector field is of this form, and this thing is a basis. So it's essentially there are going to be three cases. There are, when we consider this as a vector space over the fraction field, the case of dimension 0, the case of dimension 2, and the case 3 that is going to be the case of dimension 1. Okay. So since these vector fields, these x and y, are going to generate this space, because this space over this vector field has dimension 2. Over C has infinite dimension, but over the fraction field of the ring of formal power series, it has dimension 2. So if you have any C that belongs to G, it can be written in a unique way as F times X plus G times Y, right? And F and G obviously belong to the fraction field. We want actually to understand how, what are the properties of these coefficients F and G. So we are going to use that C is in the Lie algebra, and X and Y both belong to the center of the Lie algebra. So you have that X, the Lie bracket of X and C is 0, yeah, because X commutes with every element in the Lie algebra. And so, using this formula, since X commutes with X and commutes with Y, this expression is going to be X applied to F times X plus X applied to G times Y. So that means, since X and Y are linearly independent over the fraction field, that these two coefficients are actually 0. So both of them are first integrals of the vector field X. In an analogous way, of course, you obtain that the Lie bracket of Y and C is 0, and in the same way, if you want, I can write it down. Yeah, is this? Yeah. This implies that F and G are also first integrals of the vector field Y. But X and Y are linearly independent. The space generated by X and Y is the same space generated by the partial with respect to the coordinates, I don't know, to a system of coordinates previously fixed. So that means that when you apply this derivative to F, it has to be 0, and when you apply the derivative with respect to the second variable, it has to be 0. So F and G are constants. And then this is obvious because this algebra is an algebra of vector fields that commute. I mean, it's linear combinations of vector fields that already commute. So we get that every Lie bracket is actually trivial. And this Lie algebra is meta-abelian, obviously, because it's abelian. So we didn't do anything difficult here, anything at all. The last case that we have to consider is the case 3, in which the center, when you consider this, the linear subspace in here generated by the center, it has dimension 1. It can happen too. If you want to write it in a slightly different form, it means that there exists a formal vector field in G such that every element of the center is a multiple of X. Right? Obviously, if you can consider also the set of vector fields of that form in our Lie algebra. And this, I use the letter I because it's an ideal, right? If you apply C that belongs to G to every element, and you consider Fx that is in I, remember that X belongs to the center, so it commutes with C, and that implies in particular that the Lie bracket of C and X is going to be that belongs to I, because it's a multiple of X. So this is an ideal of our Lie algebra, I. If I coincides with G, and it's, before that, we can say something more about I. I is an abelian Lie algebra. Because if you consider Fx that belongs to I, you have that this commutes with X because everything does. And this is X of F applies to X. So for all elements in I, this is the first integral of X. And obviously, things are going to commute. This behaves as a constant for this vector field. So it's a version of this case in which we are considering linear combinations over C of vector fields. Here is, we're considering linear combinations where the constants, where these things, even if it's not a non-constant function, is constant for the vector field. Okay? So EI, is abelian. It's an abelian ideal of the Lie algebra G. Now, if I is equal to G, okay, nothing to prove here because G is already abelian, so I is already abelian, so G is abelian, and we are done. So the problem is if they're not the same. But now you can consider this Lie algebra over here. I is an ideal, so we can consider the quotient. And since G is an nilpotent Lie algebra, the quotient is also going to be nilpotent and non-trivial. So it contains an element in the center. So that means that there exists Y, a vector field, formal vector field that belongs to G minus I, such that this belongs to the center of this Lie algebra. This condition is just to guarantee that the element is non-trivial. And now, Y is not of the form F times X, because Y does not belong to I. So it's independent of X. So again, if you have an element in G, it's of the form F times X plus G times Y. This formula over here works in the exact same way because X commutes with everything. So you're going to have that X of F and X of G continue to be 0. That's an... And if you consider the quotient by the elements, and what happens when you consider the Lie bracket of Y and C? It has to belong to I, because this is in the center of this, so this thing commutes with everything modulo I.
Javier, excuse me. Couldn't Z be a multiple no, parallel to X without being a multiple of it? In case that X has
Could be a
codimension 1
multiple of
0?
what, sorry?
couldn't it be the case that Z is a multiple of X, or multiple, no, parallel to X, but not a multiple of it? I'm thinking the case where X has codimension 1 zeros. So.
Yeah, but F is not, you're omitting denominators. These Fs are not power series, are in the fraction field.
Oh, they're in the fraction.
Okay, yeah. Otherwise, yeah, I agree with you that there is. Yeah, I didn't want to remark, but yes, it's true that you cannot, because every, I don't know, these two things are linearly independent in this vector space, so they generate the whole thing. But if you consider, for instance, the parcel with respect to X, the coefficient is not a formal power series. To introduce the fraction field is a way of not dealing with denominators. There is a universal denominator, so it could be done that way, but I think this way is easier. And the point is that since y commutes with x, this is going to be y applied to f times x plus y applied to y times y, and this belongs to I because of this condition. So in particular, y applied to y is 0, so y is annihilated by x and y, so y is constant. It's a constant function. So the point is, it's very, very simple. Here you have constants. When you, let's say, consider the quotient by this, you have something abelian, right? Because it's multiples of one vector field. So that means, in particular, that the first derived Lie algebra of G is going to be contained in I, and we already said that I is abelian. So the second derived algebra is contained in the first derived algebra of I, which is 0. And this ends the proof. For H, I have to remind you that we are not working with the initial group G, but with a finite index subgroup H. It's not G. So this is the Lie algebra of the closure of H. So this proves that H is metabelian. And now, okay, I wanted to introduce a result that I think it's very easy. This allows to prove the theorem directly for one particular case, but that it's a case, I don't know, maybe even generic, which is the following. I'm going to first consider a statement, a theorem by Jennings. I don't recall now if it's the 1950s or the 1960s, but around that time. And that says the following. Every finitely generated nilpotent torsion-free group is isomorphic to a subgroup of the, I think the name is the lower unit triangular group. For some dimension, right? What is this group? Is the group of matrices or operators that are lower triangular, right? But all elements in the principal diagonal are equal to 1. This is obviously a group. So every finitely generated torsion-free group if it's nilpotent too, it's always, there is, and this is built even explicitly. What is torsion-free? If you have, you can define the subset of torsion elements of a group, which is the set of elements of the group such that there exists, for instance, a positive integer such that f to the power k is the identity element. And in the case of nilpotent groups, the set of torsion elements is also a subgroup. It's a normal subgroup. For a general group, it's not a subgroup necessarily. And we say that it's torsion-free if this group over there is trivial. So that the unique torsion element in the group is the identity element. And why I wanted to introduce this result? Because I think that it's connected to the things that we were talking about the first day. We were introducing linear algebraic groups. And here you can actually prove the theorem for some cases by coming back to the linear case, to the case of finite dimension, the case of linear operators of a finite dimensional complex vector space. So we have that H is a finite index subgroup of G, and that H is meta-abelian. But we can consider G now. Well, let us suppose, of course, something. Let us assume, I'm going to do the proof just in this case. Let us assume that G is torsion-free. I'm not going to write down the details for the torsion case, just for the torsion-free case. But it's not very different. I mean, the techniques are similar. It's just, there are other arguments, but in the same family, let's say. So let us assume that G is torsion-free. We can then assume that G is actually a group of a subgroup of lower unitriangular matrices, because these properties, being meta-abelian or nilpotent or solvable or whatever, yeah, are preserved by isomorphisms of groups. So we are going to work in the lower unitriangular groups. So we can suppose that G is contained in unitriangular N for some N. This N, obviously, the number of dimension of the matrix depends on the group. And there, we are back to unipotent. We are going to consider Zariski closure, but not in the group of local diffeomorphisms. We are going to consider the Zariski closure in here, in the lower unitriangular group. So in that group, all operators are unipotent. And so what we have is that we know that, considering the closure over there, this is not, I'm going to write it down explicitly. We consider the Zariski closures in this lower unitriangular group from now on. So what happens? Since everything is unipotent, you have that because it's unipotent, the closure of G is equal to its connected component of the identity. We saw that in the first lectures. But from here you get that the closure of H is a finite index in the closure of G. So in particular, it contains the connected component of the identity. So these things are all the same. And now you have that if H is met-abelian, this happens if and only if the Zariski closure is met-abelian. These properties are preserved when we go to the Zariski closure. This happens if and only if the closure of G is met-abelian, of course, because these two groups are the same. And this happens if and only if G is met-abelian, again, because meta-abelianity is preserved when you go to the Zariski closure. So in particular, that this ends the proof for this case. If it's non-torsion free, it's a little bit more complicated, but then you have more structure to play with, because now the elements in the torsion group are special, because you have rotations in, yeah, you have elements of finite order that are real analytic diffeomorphisms of the sphere, so they are conjugated to a rotation by a rational angle or whatever. So the point is, you can use this structure. For instance, you can use that these rotations have just two fixed points. To play with these two fixed points, you have in that case a finite orbit with two elements, and it's possible to do something a little bit more complicated, but not much, to prove that it's still true in that case, the result. But the idea is, if you see the whole thing that we were actually trying to prove when we got to Lie algebras is completely trivial. I did the proof completely not because it's difficult, it's not, but because I think it's interesting to see that you can explain it pretty easily, and there is no argumenting here that is complicated. The main idea is getting there. It's the reduction of the problem. That's an idea of GIS that is pretty good, actually. But once you get to Lie algebras, the equivalent problem is trivial.
Is this the original approach? Is the approach using the original proof?
Yeah. It's there is another argument for the torsion-free case, but using lattices. But yeah, it's essentially the same thing. That finite index subgroups. The idea is you have a finite orbit. If you are in the torsion-free case, you don't care about what the size of the finite orbit is, because you can consider a finite index subgroup and work there, and so you can suppose that the finite orbit is a fixed point for everyone. If it's not torsion-free, he proves that the orbit has at most two elements. And two is a little bit worse than one, but you can multiply the arguments by two, let's say, and it still works. Indeed, he has something like that. He has a notation like this at some point. Because he has to consider germs in both fixed points of the rotation. So you have two germs and not one. That's the reason I say that the arguments are somehow multiplied by two. I don't know if I have time. Okay, I think I'm going to state a result, but I'm not going to prove anything, because I suppose that you are tired. And something that I wanted to say is that you can apply also these things to because here you could say, okay, this is natural. We are actually working, trying to understand what the structure is of a group, right? Algebraic properties of the group. So if you have a study of algebraic properties of local diffeomorphisms, it's not very surprising that these things are connected. But you can use this in other cases, for instance, for dynamical properties, to find non-discrete orbits. So the theorem is just to have a taste of what we can find, is you consider a non-solvable, something that I didn't define yet, but it's an algebraic property. It's, if you want the, well, it's a generalization. I prefer not to. I can explain later, but somehow a generalization of abelianity that is different than nilpotent. And consider a non-solvable subgroup that is contained in the set of unipotent diffeomorphisms, right? Why unipotent? That I can explain is because unipotent groups of diffeomorphisms are connected, so they are very well represented by their Lie algebras, and this thing is proven by going to the Lie algebras exactly as in the Gist theorem. Obviously, the proof is not the exact same, it's not the same at all, but the idea is linearizing the problem. And so what happens is that there exists a finite subset, a subset, if you want, of generators of some subgroup of G, an open neighborhood B of the origin and a sequence which is defined in B of elements that belongs to the group generated in G by the finite subset S minus the identity element that converge such that you have that the limit in B of the Fn is the identity. And this is uniform convergence. So in particular, all points in B except maybe at most a countable, except at most a countable union of proper analytic sets are recurrent. Their orbits are non-discrete because if you pick a point P in B, this tends to P, so the orbit is non-discrete. That's the reason we are asking here that the Fn's are not the identity, so that these elements are generically different than P. And so, okay, I'm going to, so this is, what this result is true for n equal 2 is a result of Rebelo and Reyes. And for n greater than 2 is a result of mine. Okay? And Nakai?
Yeah. N equal 1.
Ah, sure, yeah. N equal 1. Yeah, yeah. But Nakai, yeah, Nakai. You are right. Exactly, exactly. Well, in dimension 1, you have a much more accurate description of what goes on. But sure, yes, in dimension 1, it's a result of Nakai. It's a consequence of its description of non-solvable groups of groups of tangent.
Yeah. It's part of the proof.
Yes, yes. So, okay, I'm not going to tell how to prove this, but very, very, very succinctly, what you're getting here is you get a way of constructing a sequence of elements. I'm not going to explain exactly how, but it's not difficult. It's based on the fact that the group is non-solvable. So you construct this sequence over here, right? And at some point, the issue, constructing this sequence is not very, very hard. It's based on estimates of Rebello and Frank Loret. But the issue is, at some point, you have to ensure that this sequence that you are trying to construct in general does not consist just of diffeomorphisms that are equal to the identity. And in order to do that, you need to work with the Lie algebras. You need to understand the structures of the Lie algebras of the subgroups that appear in the construction. And because that's the hard part of the proof. The hard part of the proof is not constructing the sequence that converges uniformly to the identity. The hard part, I think, is proving that this sequence actually does not stabilize. And that's where a fine study of the Lie algebras appear. So thank you very much.
Thank you. Thank you, Javier, for the beautiful series of lectures. We have time for questions. Anyone? Do you see raised hands in your side, Frank?
Yes.
Maybe it's a silly question, but why in the theorem of Gies the group is finitely generated?
It's not. It's the problem of going too fast, but it's not. But it's because it's not. It's not. Good question. What happens is that I defined all these series in previous lectures. I defined, for instance, the first subgroup of the descending central series, the derived group. I defined all these. Okay, I defined this. Okay, but what's important in all these definitions? Here, you are considering, when you consider the derived subgroup of G, for instance, the group generated by the commutators. Right? But the commutators only involve two elements. So you could actually, what you have is that the derived group is actually the union for every H, which is a subgroup of G that is finitely generated, of all the derived groups of the H. And the same thing, and if you go to the second derived group, what are the generators of the elements of the derived group are products of commutators, which are going to involve a finite number of elements. When you consider commutators of those things, the number of elements is going to increase, but it's still going to be finite. So all the commutators that you get involve always a finite number of elements, and because of that, you have also that the second derived group is the union of the second derived groups of the
Is the union or the group generated by the union?
Okay?
Is the union or the group generated by the union?
No, it's the union. It's the union.
I don't think so.
No? Yeah.
Because G1, G2 are already not the commutators, right? They are the group generated by commutators.
Yeah, but...
not every element in it
But
can...
it is the same. I mean, if you have here a product of commutators, if you have this, this is in the group generated by these four. I mean, if you consider a sufficiently enough big finitely generated group, it contains all the elements of the commutator, all the elements of the product of commutators. So that's the point. The point is you prove it for finitely generated, but if it happens for all finitely generate the subgroup, this union is trivial, so the initial group is also metability.
More questions? Well, so to have 5 minutes.
I would like to know if it is possible. So you prove that your group is non-discrete in some sense because there are elements converging to the identity. And I would like to know if it is possible to construct a true vector field somewhere, like in the theorem of Nakai, a true vector field, holomorphic vector field, such that its flow is contained in the dynamics.
That, I don't know, but the answer is I don't know. It could be nice because, of course, that could give much more information about the dynamics of G, but I don't know. It's a very good question, too. I can think of that, but right now I don't have an answer.
Mm-hmm. Okay. Thank you.
Okay, I think we can thank Javier again.
Thank you, Javier.